This video covers initial conditions of simple harmonic motion. From here on out, you're going to want to think of simple harmonic motion two different ways. In our last video, we saw that a mass on a spring vibrating back and forth shows simple harmonic motion. Now, if you place a ball on a turntable and shine a light from a projector, like shown in this picture, the shadow also follows the same motion as the mass on a spring. So circular motion or uniform circular motion projected onto one dimension is also simple harmonic motion. And this is going to help us look at our unit circle. In our last video, we said that this position function represented the motion of an object that oscillated if it began at an amplitude of A. Now, when this is not true, when you do not start at an amplitude of A, then we have to introduce a phase constant, measured in radians. Now, this piece down here is the phase. This piece here is the phase constant. Now, these are Greek letter phi's, and this is phi naught. So when you do not start at an amplitude of A, then you need to include that piece in your equation. Now, if you look at the diagram over here, if we were to start at position A, phi naught would have been equal to 0. And that makes sense because it goes back to the original equation that we started with. But let's say that we do have an angle of phi naught. That means, let's say that we're starting at this position here, at an angle of phi naught. Then our new initial position is a cosine of phi. And again, what we're doing is we're looking at this triangle here. This angle is adjacent to, or this side is adjacent to. So our initial position is equal to a cosine of phi naught. So to determine the initial conditions of a situation, you simply set t is equal to 0. So your equation simplifies down to the initial position is equal to a cosine of phi naught. In our last video, we also saw the equation for velocity, which is the first derivative of position. And we said it was negative angular frequency times amplitude times the sine of, now we're adding this additional piece, this omega t plus phi naught. So when I said t is equal to 0, then what we're doing is we're solving for our initial velocity. So the first piece goes away. And all we're left with is negative omega times a times the sine of phi naught. Remember, also in our last video, that we said omega a can be replaced by v max, which is our maximum speed. Now remember that here our position and velocity are both vectors. So if we do get negative values, then it is to the left of our equilibrium position if we're talking about position. And if it's a negative velocity, then we are traveling to the left. Now let's look at a couple of examples. In this first example, what I want to emphasize is solving for our initial position. Now here, our phi naught is equal to pi over 3. So if I put the cosine of pi over 3, I get 1/2. So our initial position is 1/2 a, our maximum amplitude. In the second picture, I'm also starting at 1/2 a, but our phi naught is actually negative pi over 3. So if I do the cosine of negative pi over 3, I still get that 1/2. So my initial position is still 1/2 a. So here we are traveling in a different direction, but again, all this equation tells me is my initial position. And the last picture, my phi naught is equal to pi. So if I were to put pi, cosine of pi into my equation, then I would get -1. So my initial position is negative a. Now if we look at the velocity function, again, what this tells me is the direction that I'm traveling and the speed that I'm traveling at the beginning. So looking at the first picture, if I were to put phi naught of pi over 3 into this equation, I would get the sine of pi over 3, which is a positive number. But I already have a negative there. That means my initial velocity would be negative. And that makes sense because here in our diagram, we do see that we are moving to the left at that point. In our second picture, I have a phi naught of negative pi over 3. So again, if I were to put that into my sine function, I would get a negative value. But I already have a negative there. So then my initial position, or my initial velocity, would have been a positive number. And for my last example, I have a phi naught equal to pi. So if I put that into my equation, sine of pi gives me 0. So my initial velocity, if my phase constant is pi, is 0. So basically, if our phase constant is between 0 and pi, then our v naught is going to be negative. That means we are moving to the left. Again, what you're doing is you're looking at the different positions here. You can actually imagine that my block here is moving to the left this entire time. That means after we've passed pi, now our phase constant is between pi and 2 pi, or another way to say that is negative pi and 0, which means that we are moving back to our amplitude of a positive a. So what we're doing is at this point, we start moving back in this direction. And again, the whole cycle starts over once I pass 0. So between 0 and pi, our velocity is negative. Between pi and 2 pi, our v naught is positive. In a little bit, we'll show how to solve for the phase constant mathematically, but we need to also be able to get this information from a graph. So if we look at this function, or this picture here, this graph represents our position function of a cosine omega t, where our phi naught is equal to 0. So that's what our function shows here. And you can actually practice putting some of those numbers into the calculator and graphing it just to prove it to yourself. Now we can see here that a complete period would be at this point. So this is when we have reached 2 pi. Another way to imagine it is if we look at this unit circle, I'm going to draw this middle point right here will be my equilibrium. I'm going to start as the amplitude of A, and I'm going to oscillate about my equilibrium position. So at one point, I've reached a negative A. At the other point, I've reached a positive A. So let's say our graph actually started here. This is where t is equal to 0. Now you can see at that point, which is here, my phase constant would be equal to pi over 2. Let's say my graph started here. Let's do another color here. Let's say my graph started here. Then that point is shown over here, where my phase constant would be equal to pi. And let's say that we had our graph start at this position. Then we can see that our graph would be at this point. Now, instead of saying pi over 2, because we are not moving in this direction anymore, we're actually moving backwards, we're going to say that our phase constant is either 3 pi over 2 or negative pi over 2. Because again, we want to make sure that we can show that our position function is here in the middle, but that we are also moving backwards. And then let's say that we had our function start here. Well, it's the same as it was at the beginning, so our phase constant would still be 0. In this example, we have an object on a spring oscillates with a period of 0.8 seconds and an amplitude of 10 centimeters. At t is equal to 0 seconds, it is 5 centimeters to the left of the equilibrium and moving to the left. What are its position and direction of motion at t is equal to 2.0? Now, first off, we need a label of our information. We know that the period, which is capital T, is actually 0.8 seconds. The amplitude, A, is 10 centimeters. And we can convert this to 0.1 meters. At t is equal to 0, my position, my initial position, is 5 centimeters to the left. Because it's telling me it's to the left of equilibrium, that says that my phase constant has to be between pi over 2 and pi. This means that it's moving on the top half of our circle, or between negative pi and pi over 2. Negative pi over 2. Either moving at the bottom half of our circle. So again, what I'm referring to, if this is our unit circle, and it's moving, it is to the left of equilibrium, which is here in the middle, it has to be in either of these two shaded areas, which is pi over 2 to pi or pi to negative pi over 2. It has to be one of those two areas because it is to the left of the equilibrium. But now it's telling me that it's also moving to the left. So if it's moving to the left, it has to be on the top part of this circle. That means that we have narrowed it down to just this top section. So my phi naught has to be between pi over 2 and pi. So we can solve for phi naught using our given equation, which was x naught is equal to a cosine of phi naught. Again, this is true when t is equal to 0. I want to solve for phi naught, so we divide by a, and then get the inverse of cosine. To give us phi naught. Again, we know all these values, so I can substitute them in. So this is cosine inverse. X naught, it did tell us again we are to the left of equilibrium, so really I should have put a negative over here. So it's a negative 0.05 meters over 0.1 meters. In this case, it wasn't absolutely necessary to change the units. They would have canceled out either way. And I get 2 pi over 3. And really we should label this as positive 2 pi over 3 and negative 2 pi over 3, because we can achieve this initial position of 0.05 either way. But looking back at the information that we talked about at the beginning, I've already narrowed it down between pi over 2 and pi. So that means that my x value, or my phi naught, has to be positive value. So again, now we have a value for phi naught. Now what this problem is asking for is what are its position and direction of motion at t is equal to 2.0 seconds. Now, all of this is to eventually get an equation for position. So going back to our original function, once I know the last piece of information, which in this case is omega, once I know omega, I can plug in t is equal to 2 seconds and get my position at 2 seconds. So in order to do that, I need to say that omega is equal to 2 pi over t, which is what we saw in our last video. That omega is 2 pi over 0.8 seconds, which is going to give me a value of 1.87. I'm sorry, 7.85 radians per second. So again, this is my value for omega. So I can rewrite my position function with all of my given information. And now my solved omega. So again, the amplitude was 0.1 meters. Omega is 7.85. I want to go ahead and just put t back in there so we have a general function. And my phi naught is 2 pi over 3. Now I can evaluate this function at t is equal to 2 seconds. So I get 0.1 cosine 7.85 times 2 plus 2 pi over 3. And that's going to give me a position of 5 centimeters, or 0.05 meters. This is 2. Now, because this is a positive value, that means we are to the right of my equilibrium position. Again, because this is a positive value, we are to the right of my equilibrium position. But that just means we can be found at that position. That doesn't necessarily mean we're moving to the left or right. But we also want to know the direction that we're moving in. So for that, we can look at our velocity function. So if we're trying to solve for our velocity at t is equal to 2 seconds, it's not necessary to solve for the initial velocity, because we can also substitute. So let's write this out. We know that our equation for velocity is negative omega times a times the sine of omega t plus phi naught. And if we wanted to solve for the initial velocity, then we can use this function instead. But again, it's not absolutely necessary to solve for the initial velocity, because we can use it based on the information that we already solved for. So our velocity at t is equal to 2 seconds is negative. Our angular frequency we solved for is 7.85. Our amplitude was 0.1 meters times the sine of 7.85 times 2 for 2 seconds plus our phi naught, which we've already solved for, which is positive 2 pi over 3. When I plug all of that information in, I'm going to get a positive 6.68 meters per second. Again, this is my velocity at time is equal to 2 seconds. Because this is a positive value, this means we are moving to the right. And then a few more things. We can also solve for our acceleration function, which, remember, is the derivative of the velocity function with respect to time, or the second derivative of the position function. So again, our function for velocity was negative omega a times the sine of omega t. And if we take the first derivative of that, then we get negative omega squared times a times the cosine of omega t. Now, if we needed a phase constant, we can just simply add a phase constant here and add a phase constant here. Again, because they're constants, it doesn't affect the derivative. So if our acceleration function is negative omega squared times a cosine of omega t, well, you can recognize the second part of the equation as simply our position function. So if we needed to, we could replace that section with just x. So what this tells us is that acceleration is proportional to the negative of the displacement. Meaning where position is maximum, acceleration is minimum. When position or displacement is minimum, when you have negative xa, then you have a maximum acceleration. And then finally, we are going to derive all of these equations in our next video, but for now, we just want to get some practice using them. So here we have two equations that we saw last year. We have the period of a mass spring system, and this is either a vertical or horizontal mass spring system, where m is equal to mass, k is our spring constant, and capital T is period, omega is still angular frequency, and f is regular frequency. Down here we have the period of a simple pendulum, which is simply a mass on a string, and T is equal to period, L is the length of the string, and G is positive gravity.